Okay, welcome in here. We are going to do an example problem figuring out if the derivative exists at a point in question, in this case, some value c. So I've been given, not the graph, but I've been given a piecewise function here, and I'm going to go through two different examples, one after the other. Let's see if I can zoom in on this. So determine whether the function f has a derivative at c. And we're going to go on question A first here on the left. So what do I need to figure out? In a previous video, in an explanation, I talked about what the graph looks like. So when we think about that, does the derivative exist at this value c equals -1? Well, in order for that to happen, we definitely need it to be continuous, okay? We need the graph to be continuous at that point. Hopefully that makes some intuitive sense. If just the regular, before we take any derivatives or anything, if the left side and the right side don't match up in the regular function before we take a derivative, the derivative definitely won't exist, okay? So let's just check real quick to see if there's a clean handoff, so to speak, in my original function. And the way that I'm gonna do that is I'm just gonna evaluate what happens at -1 in each part of the function. So I'm going to look at my first piece, which is 4 minus 3 times x squared, and I'm going to evaluate that at -1, and I'm going to see what I get. And I would like that to be the same value when I evaluate the other piece at -1, right? So I'm plugging in -1 for both, and I'd like to make sure my y values are handing off at the same spot. So as I'm traveling along my graph, I want to make sure that the y values are at the same spot. They're matching up. They're not getting like 7 and 3, okay? So when I plug in -1 in the top, I get 4 minus 3 times -1 squared. So -1 squared is 1, times 3 is 3. 4 minus 3 is 1. That's what I got for that piece, okay? -1 cubed, and then the negative of that. So -1 times -1 times -1 is -1, and then a negative of that is 1. So that works out. That's really nice. When I plug in -1 for each one of those, I get an output of 1. All right, so that's great. I know it's continuous. I know that the limits as x approaches -1 will work out really nicely because both pieces of my piecewise function are continuous. They're just regular old polynomials. You can see that. So that works. That checks out. This is good. This is good. This tells me it's continuous. Okay, so that's really nice. Now what I want to do, because just because it's continuous doesn't mean a derivative exists. We've looked at examples like that before. So now what I want to do is I want to check to see what happens with the derivative. In other words, what happens with the slope as I'm approaching -1? Is the slope going to be the same? Is it at the handoff? So I've analyzed the y values as my x values approach -1. I'm now going to analyze the slope. So what I'm going to do is I'm going to take the derivative of this top piece here. I'm going to take the derivative of that, and I'm going to get, so it's kind of like this. This is, think about it this way, f prime of x, the derivative is going to be, let's see, the power rule, so bring down the 2, so -6x if x is less than -1. And I'm going to put less than, I'm not going to put equal to because I'm not really sure about this yet. This is just kind of like a little guess here. And now I'm going to find the derivative of the second piece there. So -x cubed, I'm going to bring the exponent down. That's going to be -3x squared, okay? And that's when x is greater than -1. I haven't underlined anything because this is just kind of a thought experiment. I really want to see what happens as my derivative approaches -1. I want to make sure the slope hands off in a clean way. So what would happen at -1 with these derivatives? Okay, so if I plug in -1, I get 6 for the top piece. If I plug in -1 for the bottom piece, I get -1 squared is 1 times -3 is -3. That ain't good. That's telling me that the slope at -1 for the top piece is 6. So I've gotten to 6. But the slope on the other piece is going to -3, right? So my slopes are adjusting really rapidly at that handoff of -1, and that's not good. That means there's some sort of like corner in the graph somewhere. So it's continuous, we knew that, but the slopes are not handing off in a clean way. The slopes are not handing off in a clean way. So in other words, the limit as x approaches -1 of the derivative f of x does not exist. Okay, so because the left hand and the right hand side of the derivative doesn't work, so that ain't good. You could think of it as this. You could break it up a little bit more because I'm talking about two different pieces here. So -1 from the left is not equal to the limit as x approaches -1 from the right of that. And that's really just showing the left and the right side, which is the derivative, right? The derivative piecewise function that I drew. That's why I didn't draw the underline, and I'm glad I didn't, because the derivative does not exist. So that part is going to tell us that it is not differentiable. The derivative does not exist at x equals -1. And that's really my final answer. The derivative does not exist at x equals -1. Alrighty. So let's see a different example, and I'll go through it a little bit quicker where it does work out really nicely. So I'm going to do this over here on the right. Let's see if I can zoom in okay on that. Zooming in, I don't know how well that'll work. Okay, so I've got this piecewise function. Now my c value is 1. So essentially what I want to do is make sure it's continuous. So I'm going to plug in 1 in both of these. Make sure I get the same thing. 2 times 1 is 2, plus 3 is 5. 1 squared is 1, plus 4 is 5. So it's continuous. That's good. And then I want to take the derivative of each piece, and then I'm going to plug in 1 to see if I have a nice handoff in slope. So the derivative of the top piece is going to be 2. The derivative of the bottom piece is going to be 2x. All right, and again, I'm going to put x is less than 1 and x is greater than 1 for now, because I don't actually know if I should underline it. I don't know if the derivative exists at 1 yet, but I'm going to plug in, I guess I don't need that f of 1 yet. I'm going to plug in 1 into the top, and I will get, let's see, I'd get 1. And then if I plugged in 1 in the bottom, I'd get, oh, I lied. I would not get 1. Sorry. If I plug in 1, there's nowhere to plug it in, and I just get 2. If I plug in 1 in the second one, 2 times 1 is 2. So yes, I will have a derivative because my slopes are approaching the same value of 2, right? My derivative is the slope, and my derivatives, when I took the derivative of each piece, as x approaches 1 from the left and from the right, less than 1 and greater than 1, I get the same value. So I would say, because I got 2's there, yes, the derivative exists at x equals 1. What is the derivative at x equals 1? It's 2. All right, so f prime of 1 is 2, turns out. So we can see what happens there. Check for continuity first. Make sure it is continuous, because if it's not continuous, it's definitely not going to be differentiable at that point. So if you didn't get the same values there in the beginning, you don't have to go any further. The next thing you want to check is if the derivative is approaching the same value. So take the derivative of each piece and then test that point in question. Make sure you get the same slope value back out. If you don't get the same slope value back out like we did over here, then the derivative will not exist. If you do get the same value like we did here, the derivative will exist at that point. I certainly hope that helps. Good luck out there.